Welcome to iLecture Online, and here's another example of how to find the electric field. But this is a different kind of problem. Now, normally, this would require a fair amount of advanced mathematics and integration, but because we can employ something called Gauss's law, we can actually put this down at the level where integration in the real sense is not really that necessary. So, here we're going to employ Gauss's law to find the electric field from an object, in this case a conductor, a linear conductor that contains charge in the amount of 25 microcoulombs per meter. And you need to find the electric field in the presence or near that conductor, in this case 50 centimeters away. How do you do that? Well, again, to understand what we're doing here, let's draw a picture. So assume that we have a conductor, and the conductor contains a certain amount of charge. And assuming that there's no current on the conductor, so the charge is stationary, it doesn't move, we can indicate that the charge density is equal to 25 times 10 to the minus 6 coulombs per meter. And that's a symbol to indicate charge density per unit length. And at some distance, let's say right here at some distance, which is 50 centimeters away, 50 centimeters is the same as 0.5 meters. What is the electric field at this location? Of course, we'd like to know the magnitude and the direction of that field. Using a red color, we can probably assume that this is a positive charge, that the field would be emanating away or directed away from the conductor. And here we go. Let me just mark it like that. There's my electric field. And we have to make one added comment that we can assume that this conductor is almost infinitely long. Of course, there's no such thing as an infinitely long conductor, but just assume that the conductor is so long that there's no effect, that there's nothing beyond certain distance away from this conductor, so that we can assume, for the sake of the equation here, for the sake of doing the problem, that the conductor is so long that we don't need to worry about the edge effects of the conductor. Otherwise, the problem becomes a lot harder. All right, so how do you do that? How do you figure that out? Well, what you could do is you could just kind of say, well, I'm going to figure out what the electric field is due to this charge, and then due to this charge, and each time draw a vector and add it all up. You can see how that would imply that you need to do integration. But a very smart individual named Gauss came up with a very interesting technique and very interesting concept. He said that if you draw what we now call a Gaussian surface around it, which is perfectly symmetric. So in other words, we're going to draw a spherical shape, or not spherical shape, but I should say cylindrical shape object around my conductor here, in such a way that the end or the edge of my shape goes right to the point of interest where I want to find the electric field. Then he said, if you do that, you can imagine that there would be field lines, electric field lines, emanating in all directions away from all the charges. And of course, that would be so in both directions, up and down. So you can imagine that we have a situation like that where there would be an electric field emanating away from my conductor in all directions. There we go. And so we're going to draw a shape around it. In this case, it's a cylindrical shape. And the radius of the cylindrical shape, r, in this case is going to be, of course, 50 centimeters or 0.5 meters, because we want to make sure that the edge of that shape goes right through the point of interest. We can also imagine that we're going to make a very long cylinder so that the edges, again, are not important, only the sides. So imagine this big cylinder surrounding the wire with all the charge. Gauss then said that if we take the surface integral of the electric field emanating away from my charged object, multiply times the dA. dA is what we would call a small little surface element. So if we think of a little surface element right there, this would be the little dA. And of course, the little dA is equal to the little dA like this without a vector. No, I guess you can't really see the vector symbol here, so let me show the vector symbol. dA times the normal vector. In other words, imagine that every little surface element dA has a little unit vector pointing directly away perpendicular to that area element. He said that if you then multiply the strength of the electric field times the direction of the electric field at this little element, multiply that times the little dA, and you integrate that over the entire surface, that would be the entire surface of the cylinder, that is equal to the charge that's inside the enclosed surface divided by epsilon sub naught. Now you're probably saying, wow, what in the world is he saying? I have no clue, but hang with me because it's actually not that bad. First of all, this little symbol here, epsilon sub naught, we haven't seen yet, but you can say that K is equal to 1 over 4 pi epsilon sub naught. So this K that we've been using in our Coulomb's law, in the equation where we find the electric field, is related to this little epsilon sub naught, which is called the permittivity of free space. And so therefore we can say that epsilon sub naught is equal to 1 over 4 pi K, where K of course is equal to 9.10 to the 9 newtons meter squared per coulomb squared. So you can see that we can actually calculate. It's just a constant that indicates what we call the permittivity of free space, which has to do with how space allows the electric field to be effective throughout space in a way. That's one way to look at it. All right, so having said that, let me just show you how to do a problem like this, and then you'll find out it's really not that difficult. So we're going to write the equation as the surface integral of E dot dA, like so, is equal to the Q enclosed divided by epsilon sub naught. Now, what is the strength of the electric field at the surface of this cylinder? Now, imagine, since you have this line charge that has electric field emanating from it in all directions, of course, all 363-degree direction, up, down, to the front, to the back, down below, in all directions, we can see that the electric field line would be perpendicular to the surface of this cylinder no matter where we look at it. Since we multiply the strength of the electric field times the area element, and since they're perpendicular to each other, this can then be written as the strength of the electric field, which doesn't change. It's the same anywhere along the surface of the cylinder. This then becomes a constant, and so then it's E times the integral of all the little dAs, all the little surface elements of this particular cylinder, and that's equal to the Q enclosed divided by epsilon sub naught. Now, what is the surface integral, or the integral of all these little area elements for this whole cylinder? Well, it's simply the surface of the cylinder. And how do you find the surface of a cylinder? Well, if you ignore the ends and only look at the side of the surface of the cylinder, which is the side here that we're looking at, that would be equal to the length of the cylinder, however long the cylinder is, times the circumference of the cylinder, which is 2 pi times the radius. So the area of a cylinder is 2 pi r times the length, and so we can replace this by E times 2 pi r times the length equals the Q enclosed divided by epsilon sub naught. And now you can kind of see the strategy here. Ultimately, what we're looking for is we're looking for this amount right here. We're looking for the magnitude of the electric field, which is what we're looking for. The direction, of course, is always radially outward from this particular wire or conductor that has this charge on it. The only thing left to do now is to find out how much charge is enclosed in my cylinder right here. Knowing that my cylinder has length L, how much charge is enclosed in the cylinder? That's the same as saying how much charge is there on this conductor from the front to the back of the cylinder of length L. And to find the total charge, knowing that the charge per unit length is equal to this, we could say that the total charge Q is equal to the charge density, which is the charge per unit length, times the length of that cylinder. If that's true, then that's equal to the Q enclosed. So we can now say that the electric field strength times 2 pi RL, which is the surface area of the cylinder, the Gaussian surface, not including the ends, is equal to the Q enclosed, which is equal to the charge per unit length, lambda, times the length of the cylinder, all divided by epsilon sub naught. And now we have an equation where there's only one unknown. The length of the cylinder cancels out because we have L on both sides of the equation. This is just a constant. That's the charge per unit length that's given to us. We know the radius that was given to us. The only thing we don't know is the electric field strength which is what we're looking for. So we're now going to divide both sides by 2 pi r. When we do that, we have the strength of the electric field at the location of interest is equal to the charge per unit length divided by 2 pi r times epsilon sub naught. And then if we plug in the values, we can say that E is equal to 25 times 10 to the minus 6 coulombs per meter divided by 2 pi times r. Now r would be 0.5 meters. And then epsilon sub naught is the same as saying 1 over 4 pi times k, and k is 9 times 10 to the 9th newtons meters squared per coulomb squared. Oh, and by the way, since it's 1 over that, I guess I didn't write it down far enough down. Let me rewrite that. Since it's 1 over epsilon sub naught, 1 over epsilon sub naught would be the inverse of that. So that's actually equal to 4 pi times 9 times 10 to the 9th newtons meters squared per coulomb squared. There we go. Got to make sure we do that correctly. All right, now simplifying, we have a 2 pi here and we have a 4 pi there, so that becomes 2. 2 divided by 0.5, that becomes 4. And now we can go ahead and grab a calculator and find out what that is. So we have 25 exponent 6 minus times 4 times 9 exponent 9 equals, and it looks like 900,000 newtons per coulomb. So the answer is the electric field strength at a distance 0.5 meters away from a conductor that has a stationary charge of density 25 times 10 to the minus 6 coulombs per meter, or 25 microcoulombs per meter, is equal to 900,000 newtons per coulomb in a direction radially away from the conductor. Now, of course, if I consider a point directly above, then of course the electric field will be upward. If I consider a point directly below, the electric field will be downward. If I consider a point out here, 0.5 meters in front, then the electric field would be away from us. And if I consider 0.5 meters into the board, then the electric field would be into the board at that same magnitude. So it's the radially outward electric field of magnitude 900,000 newtons per coulomb. And that's how we solve a problem like that. Now, again, doing a quick review of Gauss's law, Gauss said that if you can come up with a symmetrical shape object, such as a cylinder or a sphere or something like that, in this case we use a cylinder, in such a way that the edge of the surface, as we call it, is at the point of location of interest, where we want to know the strength of the electric field, then he said that the electric field strength at that surface, which would be a constant anywhere along the surface, times the area of that surface is equal to the charge that's enclosed by the surface divided by epsilon sub naught. And implementing it like this, realizing that the electric field strength is a constant all the way along the surface, and that the integral of dA is simply the area of the cylinder, which is 2 pi r, circumference times the length, and that equals the Q enclosed, which we found was equal to the charge density, the linear charge density times the length, divided by epsilon sub naught. Epsilon sub naught, of course, being related to K in this particular fashion. Plug in the numbers, and there you go. That's how you find the electric field along near a linear conductor that has a constant charge. All right, hopefully that made some sense. What I'm going to do is I'm going to show you some other examples using Gauss's law and Gaussian surfaces, and after you've seen a few of these, it'll begin to sink in. It's really not as bad as it appears in the beginning. All right, take a look at this, and good luck trying to understand it.